afternoon, and a monarch butterfly fans itself half-heartedly. The feeble beat of its wings stirs the air. And the faint draft ripples through the nearby fields. Amplified over distances, the current of air picks up speed. And builds to the power of a flash storm. The cautious monarch tests the new headwinds momentarily, then leaps like an airborne hound to track the fresh scent of nectar. Normally, we expect storms to toss butterflies about, rather than butterflies setting off storms. Yet small events can trigger large ones. Known as the butterfly effect, the theory suggests that each organism can influence the environment. Observation, however, more often reveals that the environment controls life. Life moves and reproduces in tune to the change of the seasons. In order to understand the relationships between life and the environment, we need a map, one that treats the planet as a three-dimensional figure, composed of a series of shells or spheres. The geosphere, the hydrosphere, and the atmosphere. The bottom sphere, the geosphere, is the ground beneath our feet. The second sphere is the hydrosphere. It consists of all the water on the Earth, including groundwater, surface water, and water vapor suspended in air. The third sphere is the atmosphere, which is the blanket of air surrounding the planet. These are the foundation spheres. But on a living planet, there is the fourth sphere, the biosphere. That zone occupied by organisms which invade the three other spheres. The biosphere begins at the bottom of the ocean floor where colonies of strange creatures bask in the boiling waters of volcanic vents. This spider is setting its silk chute to catch a favorable wind and hitch a ride on a jet stream to the upper limits of the biosphere. With our three-dimensional model in hand, let's engage in a mind experiment. Imagine that the spheres are riddled by wormholes. Coming and going in endless fashion, worms work their way in and out of these spheres through imaginary tunnels. In this model, the spheres are merely parts of one large system. But we know that worms cannot wriggle their way into the upper clouds. So, we'll replace worms with materials that can be shuffled in and out of our imaginary pathways. And this is what we observe in the real world. Thousands of different chemicals shuttling back and forth between the spheres. We'll remove all chemicals except carbon. Good choice, because carbon is the backbone of all plant and animal life. Like all atoms, carbon is a miniature power pack. But what makes carbon special is its eagerness to combine with other atoms. As well as other carbon atoms, to form long chains called organic molecules. Now these organic molecules pack a lot of energy, enough to power life. Where then does life tank up on this energy source? While the planet is a large storehouse of carbon, containing trillions of tons of carbon, only a very small fraction is available to life. And this fraction is in the form of a gas called carbon dioxide, or CO2, that floats freely between the atmosphere and the hydrosphere. Yet it is of no direct use to animals. Breathe it as they may, animals can't get at the carbon in carbon dioxide, because animals lack the key that unlocks carbon dioxide. The CO2 molecule contains a carbon atom and 2 oxygen atoms held in a tight grip. But the tough job of extracting carbon from CO2 can be handled by plants. CO2 enters the leaves, and through a reaction called photosynthesis, plants break down the CO2. This reaction, of course, is constantly powered by the energy of sunlight. So each plant is a small-scale refinery that reprocesses carbon into sugars. Life then becomes a waiting game for plant eaters, the herbivores. Herbivores use the plant sugars as a source of energy and release some of the carbon as carbon dioxide back to the atmosphere. Lurking in the wings are the carnivores, alone or in packs, ready to bushwhack the herbivores. But even in death, the carnivores tend to be stingy with their hard-earned carbon. Enter then the decomposers, who take their seat at the carbon banquet and return the carbon crumbs back to the environment. If we could trace the movement of an imaginary carbon atom, we might watch it locked up in a blade of grass, eaten by a cow, consumed by humans. Return to the air, to drift down once again and feed the same cow's offspring years later. In this simplified model, carbon atoms are passed from the atmosphere to the plant, to the animal, and back to the atmosphere in an endless cycle. While this exchange may be measured over centuries, it is considered a fast-track cycle. In contrast is the slow-track carbon cycle, where 99.9% of the Earth's carbon is off-limits to life. This is a mountain containing vast stores of carbon. How then did free-floating carbon get locked up into sheer hard rock? When small marine animals die, they sink to the bottom of the seas and carry their treasure of carbon with them. Their skeletons are covered by silt, layer after layer, and over millions of years, this mixture of skeletons and silt is transformed into sedimentary rock. Millimeter by millimeter, year by year, these beds are uplifted to form great mountain chains. Where eventually the process of erosion and weathering releases carbon dioxide back into the atmosphere. But that is not the only way carbon becomes locked up in rock. Sometimes, when marine organisms die, they are covered by sediments before they can decompose. Under heat and pressure, their soft body parts are transformed into carbon-rich petroleum. In a somewhat similar manner, forests of giant horsetail plants, much older than the dinosaurs, sank into swamps. And over millions of years were compressed into large beds of coal. Whether animals and plants are converted into rock, oil, or coal, this is the slow-track cycle occurring between the atmosphere, the hydrosphere, the biosphere, and the geosphere, and takes place over 100 million years. $100 million years in which carbon slowly trickles through the 4 spheres. Yet both great carbon cycles, the fast track and the slow track, make up one grand system. Over the long haul of the planet's history, the concentration of carbon has remained relatively constant in both cycles. So it was the delicate balance between the atmosphere the geosphere and the hydrosphere, which allowed life to take its fair share of carbon. Until humans began to tamper with the grand system. As we continue to destroy the forests and turn them into wastelands, a little chemical sense tells us that we are also cutting off the supply of carbon in the fast-track cycle. And as we tap the great carbon reserves of fossil fuels held in the geosphere, we are opening an Earth valve and releasing each year millions of tons of carbon dioxide from the geosphere into the atmosphere and disrupting the slow track cycle. Common sense tells us that this one-way release threatens to knock the entire planetary carbon system out of kilter, and chemistry is going to confirm our common sense. In the programs to follow, we'll examine the chemistry underlying the human assault on the environment. And it is an understanding of chemistry that will enable each and every one of us to assess the damage.